Hey, this is part 3 of 3 on building my Bayes calculator. That is it. In this video I'll have some examples of using the Bayes calculator, why you'd use it, kind of why the Bayes Theorem is kind of neat, and some examples of where it's used. This is going to be based on a talk that I'm going to make to the retired technophiles of Mainline in a week or so. So there's going to be a bit of a repeat of the first 2 videos on building the Bayes calculator, really just an overview, and then getting into showing some examples of using the Bayes calculator for doing things like predicting forest fires, deciding whether you're going to go on a picnic, and how it's useful for medical tests. This is a presentation I'll be giving to my meetup group, retired technophiles of the Mainline. In that group we usually just discuss technology and interesting new news and technical and science areas. So I'm giving this one on 29th of December, so it's probably we've probably had our meetup by the time this gets onto YouTube. So let's have a look at the Bayes calculator. So Bayes calculator, I put it together because I started getting interested in Bayes Theorem. Just a summary of that is it's named after the inventor. He was a 18th century Presbyterian minister called Thomas Bayes. And Bayes' theorem is a method of calculating the validity of beliefs based on best available evidence. And the high-level summary is you have an initial belief plus some new evidence gives you a new and improved belief, and the Bayes theorem actually allows you to quantify what that change is in belief or credence. And it's used in statistics to determine conditional probability, where one thing's dependent on another. So this is just a summary of building my calculator, and a couple of previous YouTube videos get into this in a lot more detail, so I'll just go through this pretty quickly for this YouTube video. But this is the calculator. It's hanging on my wall at the moment. It's got a big oak case, got a canvas print of the Bayes theorem that you see there. It's got LED display to show the results. It's got a big brass panel plate that mounts all the controls, and 4 sets of rotary controls to input values for the Bayes theorem. So when building this, I had some new challenges doing it. So I'd never done any surface mounts devices or SMD work. In this case, the only thing I had to do was move a jumper for the address selector on some of the OLEDs. So I had to work out how to heat up the jumper, which is just a small resistor, use some tweezers to move it from one location to the other to get the alternative address selected. For the calculator, I used the Raspberry Pi Pico microcontroller, and to start off with, while I was testing it out, I was mounting it on a breadboard to get my code right for the rotary controls and controlling the OLEDs and making sure I could actually control 2 OLEDs and a LED output all on one I2C bus. Some of the things I had to do while I was prototyping was on the OLED displays. I wanted to use a large font for displaying the values that I entered. Also be able to show alternative views of the numbers, either show them as percentages or decimal values. And like I said, I had to make sure that I could manage 2 of these OLED on each I2C bus. So the Pi Pico is pretty nice because it's got a lot of I/O in there. It has 2 I2C buses, so having 4 controls and OLEDs, I needed to be able to support at least 2 of these OLEDs on each bus, because I only had a choice between 2 addresses for each of these OLEDs. And finally, playing around with the rotary encoders. So I based the code that I use for this on a library that's already out there for rotary encoders, but I had to extend it a bit because I wanted to use the capability on these rotary encoders to also use the press button to change the significant digit that I'm updating when I'm inputting data because I've got 3 digits. So I don't want to spin this rotary encoder forever to put a new digit in. So I allowed by pressing the button to change the significant digit that I was updating. As well, I had to do some actual mechanical construction, so I had to build the box. I used some oak panels for that. So I used the miter saw to cut 45-degree angles in the panels I used for the sides of the box. You see down here where I used glued those together. I found a nice technique on YouTube where you can use painter's tape to keep the pieces together while you glue them. I also used some corner clamps to make sure everything stayed at 90 degrees, but this worked pretty well with the painter's tape, and by having it on there you also protect some of the wood from the actual overflow from the glue, although I didn't do that great a job at that. And then I did a test fit of all the pieces once I got the sides cut and the centerpiece cut, make sure that the panel and the Bayes Theorem print all fitted in the box. For the panel hardware, like I said, I used a brass panel for that. It's probably a bit thicker than I really needed, but this was a challenge because I had to work out how to cut the rectangular holes for mounting the OLEDs. For this, I was just using a Dremel and a file for getting these cutouts done. So you can see here where I overshot some of the sides and things. To get around that, I printed some 3D frames to go around the rectangles that I'd cut out to hide some of the worst miscuts here. And then once I'd cut everything out, I mounted the rotary controls and the OLEDs. You can see the back of the panel here. I also worked out how to mount the Raspberry Pi Pico microcontroller on a board behind the OLED as well. And then the final part of this project was writing the code. Again, the first 2 videos have a lot more details about this, but uses a Pi Pico microcontroller using rotary encoders with the Micropython rotary library that I enhanced a bit. Same with OLED. I used a writer.py library to be able to use larger font sizes. And I did have some problems here, so the actual rotary encoder code is interrupt driven, so as you turn the rotary encoder, it sends interrupts that updates the code. I wanted to sort of make one class that incorporated the OLEDs and the rotary controllers, but for some reason I couldn't get them both working together. So it seemed like the OLEDs didn't like working with something that was interrupt driven underneath the hood, so those 2 libraries didn't mix nicely. So I actually changed it into an event loop to show the input values that were in the rotary encoders on the OLEDs. Another thing I ran into was the Raspberry Pi Pico did not seem to respond to doing a keyboard interrupt, especially when I was in the main loop. So normally what you want to do is have the main.py start up when you turn on the power so that the code starts up automatically. But because it didn't seem to want to jump out on a keyboard interrupt, which is normally the way you get out of that code that's running, I was sort of caught in an infinite loop there where it wouldn't let me break out and actually update the code. So what I had to do was add a reset button, hardware reset button to the back of the board. So just a simple button, and inside the main loop now in this main pi, I just keep checking for this hardware reset button. If it's pressed down, then I exit the program, which allows me to make updates to the program. And the final one is really just my bad requirements. I should have looked at the formula better, but I actually run this in 2 modes. You'll see it in the example, the 2 modes that I'm using. So one's used to calculate based on the basic Bayes Theorem parameters, which just needs 3 sets of input parameters. And then there's a variation that's useful for doing drug tests where the probability, what would be probability B, is made up of when you're testing for doing medical tests, you have the chance of a true positive and a false positive. So you need to enter those two values. I thought I'd need an extra set of input rotary controls to be able to manage that, but turned out I didn't really need to. You'll see later on what I did there. So sort of the fourth input in that mode is really just a dummy control. And finally, this is the last part that I covered in the earlier videos, was just the main code that I did in Micropython. So this is in the main.py code. So it runs through, sets up the I2C buses, which control the OLEDs and the LED, sets up the LCD, sets up the OLED objects, also sets up the enhanced version of the OLED objects, where I take the OLED object and then add my certain functionality for displaying things on the screen. Sort of wraps up the basic SSD 1306 code. And then finally I set up the rotary dials, and there's mainly a matter of plugging in what I/O pins on the Raspberry Pi Pico are going to each rotary dial. And then we dropped into a main loop. So this is the one that I had trouble breaking out of before, but you see here it's checking for is reset, so it's checking for the physical button that I've now got on the board to break out of this main loop if I need to do that. Otherwise it runs through the loop every 50 milliseconds and checks whether any of the rotary dials have changed or any of the switches have changed. If they have, then it updates the information displayed on the OLEDs. So let's have a look at some examples, which is really the point of this third video. So first one, and I took these examples of some examples that are on the YouTube already, so I put the references at the end of this presentation for where you find the details for these. So the first example of using Bayes' theorem is to work out what's the probability of forest fires in certain conditions. Okay, so what's the chance of there being a dangerous forest fire if we see smoke? So you can sort of pretend you're a forest ranger, and you kind of know normally how often you get a forest fire each year. But if you see smoke, does that raise the probability that there's a forest fire there, and by how much? And you may have to do budgetary things, like if there's a certain level of chance that there's going to be a forest fire, maybe you then budget to send up a spotter plane to have a look to see if there's really a forest fire there. So the data that goes into the Bayes algorithm is shown here. So first is what we call the prior, or what will be PA. The chance that you have a dangerous forest fire is 1%, so maybe out of 100 days, one of those days you might have a forest fire. The chance of seeing smoke is fairly common, so and this would be probability B, is say 10%. So there may be other reasons for smoke other than forest fires, maybe people having barbecues or something. So it doesn't necessarily mean that there's a forest fire. And then the other probability we need to be aware of, the probability there's a smoke if there is a dangerous forest fire. So 90% of the time a dangerous forest fire will make smoke, so that's our probability B given A. So our calculation, and this is just straight Bayes theorem calculation, is the probability of smoke given there's fire times the probability of there being a dangerous fire, which is our A here, over the probability that there might be smoke. And so there I've plugged in the values. Let's enter the data in the calculator. So turn it on,
First thing, we need to enter our prior, which is just the general chance of a forest fire, which is 1%. So I press the rotary encoder to get it to the significant digit that I want to change, get it down to 1%. Next we'll set the chance that a dangerous fire makes smoke, which is 90%, and finally set the chance of seeing smoke, and our result is 9% chance of it being a dangerous fire if there's smoke. Okay, the second example, it's going to be for picnic planning. So I'm trying to decide, should I have my picnic if it's cloudy, or should I cancel my picnic if it's cloudy? So for this example, I'm going to use Bayes Theorem again, but I'm going to enter the probability or the chance of something happening as a decimal out of 1 rather than percentages. So the data I'm using is first our prior, so our prior chance or belief that it's going to rain is 0.1. Then we also have our probability that if there'll be clouds if it's raining, so 0.5 of the time if it's raining you'll have clouds. And then the third probability you need to be aware of, or our probability B, is the chance that it might be cloudy on any particular day, so it's 0.4. So our calculation this time is going to again just follow the Bayes theorem directly. The probability of rain given it's cloudy is the probability of cloud given it's raining times the probability of rain over the probability that it's cloudy. So we'll feed in the values and then look at the results on the calculator. Let's see if we should have a picnic. Let's turn on the calculator. In this case I'm going to enter as decimals rather than percentages, so I'll switch it to decimal mode. First I'm going to enter my prior, so just the probability of being rain is 0.1. And then the chance that there's going to be clouds if there's rain is 0.5. So I'll set that up as P given A. And then finally the chance that it's going to be cloudy is probability B. And the result is 0.125 chance that it's going to rain on my picnic. So the third example here shows a variation on the Bayes theorem. It's still basically the Bayes theorem. But in medical tests there's some variability in the how you interpret the test. So in a lot of cases there is the chance of a false positive, true positive, false negative, true negative. So you need to take that into account when you're looking at the what would normally be probability of B, or the evidence part of it, the probability that the test says you're positive. It could be due to a true positive or a false positive. So I sort of expanded the line for what would normally be probability of a positive result to say it's made up of both the chance of a true positive and a false positive. And again, in the links at the end of this, I have more detailed description of kind of why this happens in drug tests and medical tests, and it has to do with two of the parameters that usually come with the tests about the sensitivity of that test. So in our case here, it'd be the percentage of patients with cancer who produce a positive test, and specificity is the percentage of patients without cancer who produce a negative test. So let's have a look at the data that's used for this example. So again, we have a prior. So in our case, where we're trying to work out what's the chance of having breast cancer if you have a positive mammogram. And again, this is within a fixed specific population. And for this calculation, I'm going to use percentages rather than decimal input. I just find it easier to follow with the percentages. So again, the first part of this is probability A in Bayes' theorem, or the probability that the patient has breast cancer. And in the general population, that's fairly low, relatively low, of 0.8%, so less than 1 in 100 people have breast cancer. And just be aware here that part of this alternative version of the theorem, we need to know the probability that someone in the population doesn't have breast cancer, so it would be not A in this case, and it's really just the inverse of 0.8, it would be 99.2%. So this is where I messed up the needing 4 inputs on my Bayes calculator. I didn't really need it because I could work it out based on what A is, what not A is. The next parameter is the probability of having a positive mammogram given the person has breast cancer, and that would be the sensitivity of the test. So for mammograms, that's 90% of the time it comes up with a true positive. So that's our probability B given A. And then the last part of the formula we need is the probability of a positive mammogram given that the person doesn't have breast cancer. So for mammogram screenings, that's 7%, so fairly high rate of false positives as well. That would be probability B given not A. So the calculation in this case is probability of breast cancer given you that someone had a positive mammogram. We want to know what's the probability of breast cancer in that case. So it's the probability of having a positive mammogram given that the person has breast cancer times the probability in the population of having breast cancer. So again, that's our prior knowledge, just our general understanding of how frequent people have breast cancer, over the probability of there being a positive mammogram. And again, a positive mammogram is made up of the chance of someone having breast cancer and getting a positive mammogram, and the chance of a person not having breast cancer and getting a positive mammogram, which is our false positive side of things. So we need to expand all this, and you see down here our divisor is now the probability of, in the population, of getting a positive case if you've got breast cancer, and then the probability of getting a false positive in the population, or the remaining part of the population. So that's the formula that's going to be used in the calculator. So let's show that being done using the calculator, and I'll be switching modes in the calculator to do this. So I'm going to fire up the calculator. So currently it's in the traditional mode, so I'm going to change it to the 4 input mode, where I can put in the false positives as well. And I'm going to enter the first value, probability of A, which is our prior, which is just the probability of having breast cancer in the general population. Then the probability of B given A, or the probability of a positive mammogram given the person has breast cancer, which is 90%. And then put in the probability of getting a positive mammogram without having breast cancer, which is 7%. And we see the result is 9.3% in the population. So that's kind of a counterintuitive result. So even though our test is 90% sensitive, the result is that for this population, if you get a positive breast cancer mammogram, it's still only 9.3% chance that you actually have breast cancer. So we see the calculator showed that the chance of having breast cancer after one positive mammogram is 9.3%. So in Bayesian circles, that's known as updating your prior. So you had some prior belief in or confidence in chance of having breast cancer, which is just 0.8% in the general population after one positive mammogram. That credence or belief in having breast cancer has gone up to 9.3%. Like I said, that number is not always intuitive. Many times people assume that the sensitivity of the test is the same as what's the chance of having that particular medical problem. So we see here the sensitivity was 90%. So you have to be careful with medical tests not to treat that as the confidence level of having the particular medical problem that the test is detecting. 90% is a lot higher than 9.3%, and if you took the 90% confidence level, you might embark on some kind of therapy like chemotherapy or radiation therapy based on having much higher confidence level in having cancer than you really have. So I don't think I'd be looking to take chemotherapy if I just had a 9.3% chance of having breast cancer based on a single test. So let's have one more look here at again updating our prior. So we've updated the prior of the general population of having breast cancer from 0.8 to the population of people who had one positive mammogram. But let's have a look if we go through and do another mammogram and it comes back with a positive result as well. How does that update the chance of having breast cancer? So back at the calculator, we're going to take the previous result of after one positive test of 9.3% and plug it into our calculator as the prior now. So instead of being 0.8%, it's now going to be 9.3% chance of the person having cancer, and then update it with new evidence of another positive mammogram, so 2 positive mammograms in a row. We see now that the probability of that patient having cancer is 56%, and we could actually go through and do a third test as well to update the probability of that person having breast cancer even more, which is kind of the nice thing about Bayes calculator. Bayes Theorem is it allows you to get a valid quantitative results of looking at probabilities and conditional probabilities and the impact of new evidence on in Bayes term beliefs, probably more modern term is credences about what's the chance of the person having a particular condition. Okay, finally, let's just have a look at some of the place Bayes theorems used. So as we saw, it's used in medicine, so updating a belief in a particular diagnosis based on medical tests, and then you can choose the most effective action based on that belief and having the correct diagnosis. So as we saw with mammograms, you may not want to embark on a radical process if you just have had one positive test, but if you have multiple positive tests, and hopefully with different types of tests, maybe you do mammogram for the first test, maybe you do some sort of blood or other sort of test for the next test, so you can build up the confidence with a series of tests, and you can quantify what those confidence levels should be to reach a certain threshold before you do a certain sort of process to cure the breast cancer. So sort of questions you might ask when involved in medical tests: does it make sense to embark on a course of chemotherapy after 1 or 2 or 3 positive mammograms, or a mix of tests here? And then the same thing applies for the current tests like COVID home tests. What action should you take after 1 positive home COVID test? And should you quarantine immediately? You should take another home test to improve your confidence in the results of those tests. Should you take a different sort of test like a PCR test after doing a antigen test, which is typically what a home test is. So by having a quantitative result, you can then decide what's the most appropriate action to take after getting the results of one of these tests. Bayes is also used quite a bit in data science, artificial intelligence, machine learning areas. So it's typically used in things like spam filters, so identifying spam. So by using Bayes, you can have a filter that learns as it goes, or seems to learn as it goes. So you start off with some rule about maybe what keywords are typically in spam, and the people receiving the email can comment on whether the junk was appropriately put in the right place, or the junk mails, spam mails were put in the right place. And based on that feedback and using the Bayes algorithm, you can then refine what words and what should happen with mail coming in. So it improves over time as, in this case, again, our priors about what keywords we should look out for gets updated, and hopefully our confidence in detecting spam improves as we go along. Same sort of things happening in computer vision. One part of machine learning and AI algorithms to detect things like seeing objects. So, fairly common one you see quoted is using AI to detect things like, are we seeing a cat? And again, that's usually done by training the algorithm based on cat shapes that was fed into the algorithm using Bayes theorem along with some other processes. We can improve the confidence in that we're actually seeing a cat based on improving our priors on detecting what cat-shaped objects should look like. And again, the algorithm can improve over time as you get feedback on what actually is a cat and isn't a cat. And in business, especially e-commerce, Bayes theorem is used a lot. So kind of the proposition of how likely is it that a person with certain interests will buy my product, and you might decide to have an advertising campaign or spend some money on bringing that person in or letting them know more about your product based on the probability that they'll actually buy that product based on the interests they have. And again, that's something that can be updated over time. Update the priors based on what we're seeing as the probability that the person becomes a customer based on interests, and as we get real results on whether people become customers or not, then you can update using Bayes algorithm whether that person, what the probability is that that person becomes a customer. Another place that Bayes algorithms looked at is in neuroscience. You'll see there's a process called predictive processing used to explain how the brain works. That's one of the theories for how it works. There's more details in this link here about this, but that predictive processing approach assumes that there's layers of Bayesian inference happening, and to decide whether what we're seeing or what we're sense data is coming in matches the model, or do we update that model based on new information. So again, very Bayesian-like activity happening there. And finally, kind of a more weird one, or unusual place to see Bayesian theory used is in philosophy, even as in epistemology, which in philosophy is the study of knowledge, or how people get knowledge. And how adding a Bayesian approach to inference, and there's different types of inferences, but the one we're interested in for this is inductive reasoning. So this is the kind of reasoning where maybe you see something over and over again, and after a certain amount of time you start having confidence in that thing happening all the time. But the thing that Bayesian approach adds is quantifying that, is how much more confidence should you have in a conclusion about something happening over and over again, based on, you know, how often does it happen, how often does the results map to what your theory is on what's happening. So kind of the questions that you may approach with this is, you know, you see the sun rise between 6 a.m. and 7 a.m. 10 days in a row. The question is, how confident can you be that the sun always rises between 6 a.m. and 7 a.m. So using Bayes theories allows you to actually quantify that, so you can, instead of just saying yes or no, you're confident, or yes or no, you believe that the sun rises between those times every time, is you can have a confidence level for that based on the Bayes theorem. Same thing with swans. So if you see 50 swans in a row that are white, how confident can you be that all swans are right? And this particularly applies when you think about things in the 18th century, when if you're in Europe in the 18th century, you're probably going to see that all swans are white, and, you know, your instinctive thought is that, you know, all 100% of swans are white. But that was proved wrong when found out in Australia that they have black swans. So it's better to have a confidence level around these facts drawn from induction and being able to quantify it, rather than sort of a black and white yes or no, all swans are white. So I hope that was a useful walkthrough of Bayes theorem. I'll put this down in the description, all these links, but some other resources that I use frequently was Wikipedia's got a good article on Bayes theorem. Veritasium, guy on that YouTube channel, does a really good walkthrough of Bayes theorem, particularly with medical tests again, and illustrates exactly why the non-intuitive result is the true result, and why it matches up with Bayes theorem. As kind of a deeper dive into Bayes theorem applied to COVID testing here, another YouTube out there. Right up on where Bayes is used in machine learning. Some more about Bayesian epistemology, where things are going with that, and that also leads into discussion of how Bayes theorem might be how the brain works as well. Include this one, Bayes crazy stuff. So not all Bayes stuff you should read as and take as fact based on face value. So Scientific American sort of did an article on how Bayes has sort of got outside its comfort zone in some areas. It's sort of become a new age thing in some areas. So sort of what to watch out for when utilizing or using Bayes. The examples I used about the forest fire and the picnic came from this site here. There's more examples there. I put this link in here. There was an interesting study by a guy called Geigernizer. I think he's a social statistician, where he actually put that question and the data about mammograms and cancer tests to a bunch of doctors, and a surprising large number of them actually thought the sensitivity was what the probability of having cancer was. Things aren't actually that bad in medical circles. The doctors aren't usually needing to work things out using Bayes theorem. The test results are actually presented them in a way that it tells them the confidence level. So, but just illustrates how these counterintuitive probability problems or conditional probability problems, it's not obvious that the confidence levels we should get based on those sort of probabilities. And then my playlist for the calculator, so this is the third in the series of videos for that. This is the link to that playlist for the first and second, which has got more details about actually building the calculator.